So on the 3.5 page, what we want to do is think about what happens at generally when you're doing math with more complicated type graphs or equations. The answers that you're looking for in terms of the problem are usually going to be located at either the endpoints or the extremes of the problem of where the function is at, or it's going to be located at one of the maximum or minimum points. Those are usually where the answers are at. So that's why it's important for us to be able to locate the extrema. And so if we have a graph, we can pretty easily tell by looking at the graph where the extrema are at. So let me get the pen going here. Do this in green, I guess. So what we want to do is, ask ourselves, what's going on as you get as x gets larger in this direction here, which means as x gets more negative, what happens to y? And we can kind of see from the graph that the bigger x gets, or the further x goes in the negative direction, the more negative y gets. So we could say that as x goes to negative infinity, y also goes to negative infinity. So now this isn't representing the point. This is what the trend is as you go in the x direction. So, we've got our x behavior first and our y behavior second. So as x gets bigger and bigger in the negative direction, y gets smaller and smaller in the negative direction. Or as, the bigger negative, the smaller the number actually is. So as x gets smaller and smaller heading in the negative direction, then y is getting smaller heading in the other direction, heading in the negative direction also. Now at this other side over here, as x gets really large in the positive direction, we see also that y gets really negative. So we could say that as x goes to positive infinity, y goes to negative infinity. So that's how we would classify the end behavior there. And then the other thing that we need to talk about is this maximum point. Now, this is at least a relative maximum, but you can see from the graph that this is absolutely the highest point that the graph gets to before it turns and heads back down again. So we call this the absolute maximum. Otherwise, it would be a relative max, and we'll see that on the next graph. So it's an absolute max, and that absolute max is at the point -1, -2, -3, -4, 1. So there's an absolute max at -4, 1. And we've basically we've located and classified the extrema of the graph. So as x gets really negative, y gets really negative. As x gets really positive, y gets really negative. And as x gets closer and closer to -4, we see that y is getting closer and closer to 1. And actually, when it hits -4, y is actually the absolute highest that it gets. So if we want to talk about the domain and the range, which is also important, the domain, which deals with the x's, and again, using interval notation, x can go from negative infinity to positive infinity. Or we could say it's all real numbers for x. Any number can go in for x. But for the range, we're talking about y is going to always be less than or equal to 1. So we could say y is less than or equal to 1. The highest that y gets on the graph is a positive 1. Okay, so that's how, so those are some things that we need to bring out that goes with a graph that looks like this upside down parabola. Let me switch colors here, and we'll look at the second one over. So here we have a what looks like an absolute max. This is a relative min, and here's a relative max. If we just talk about those first, this is absolute because it's absolutely the highest one on the graph, highest point. This is relative because relative to the area that it's on, that, you know, relative to the area on the graph that it's around, it is like the lowest point. So it's a relative min, and here's a relative max. So that's how we would classify those extrema points there. Now, and then we would put the coordinates in. So the relative max, which is the last one that I did, is looks like it's got an x coordinate of 3 and a y coordinate of 1, 2, 3, 4. So 3, 4. At 3, 4, there's a relative maximum. At 1, 1, there's a relative minimum. At negative 2, 3, okay, and I may be counting wrong on here. Okay, so looking at the scale here, they're going by twos. So they switched the scale up on us. So this is actually a half. Let me get the eraser here. And this one's going to be off also then. Okay, so counting by halves, at 1/2, 1/2, there is a relative min. Rel min. At 1/2, 2, so 3/2, 2, there's a relative maximum. At negative 1, 3, there's an absolute maximum. So we took care of the maxes and mins, the turning points in the graph. Now we have to talk about what goes on at the extremes. So we can see that as x gets really, really large in the negative direction, as x gets more negative, y is going to be heading down and getting more negative. So in terms of well, let's talk about domain first. So in terms of the domain, x can be all real numbers. And in terms of the range, the absolute max is where y is equal to a 3. So all the y's are going to be less than or equal to 3. So we took care of the domain and the range part of what's going on. Let me get a different color here for the extremes. And then at the extrema now, we could say that as x goes to negative infinity, y also goes to negative infinity. So that's what's going on that end. And on this end, as x goes to positive infinity, as x gets really, really big in this direction, y is going to be getting really, really small, heading in the negative direction. So there we have everything classified on the graph. We've got the extremes on each end classified, and we've got the turning points, the peaks and the valleys classified on the graph. Okay. Does anybody have any questions? Like if you have a question, put it in the chat. I'll try to monitor it. But other than the notation, it's really kind of pretty straightforward, I think. And we don't really have this interval notation that we have is not really the best. So it kind of like goes both ways. If you're talking about a relative minimum point, this actually represents the point x, y. But if you're talking about a range of values, like what's going on trend-wise, this means that x, well, this is really, think of a better way to, we'll just leave it with this for right now. So trend-wise, we can see that as x gets really big, y gets really small. That's kind of what that notation means. So relative to how you're using it, we need to kind of interpret it different ways. It's like mathematical grammar. It kind of depends on the context that you're using it in to have it make sense. So there isn't actually a point, negative infinity, positive infinity. Infinity is like a concept. You're heading in that direction, but you never can actually get there. No matter how big of a number you can think of, you can always add one to it. Therefore, you can never, ever get to infinity. So it can't actually be a point. It's more like a direction that you're traveling in. So you have to kind of think about this movement along and what's going trend-wise with the other variable. So let's look over here at 15. Let me switch back to green, I guess. So on 15, we have a absolute min absolute minimum at 1, 2, 3, at 3, negative 3. So we have an absolute minimum there. We actually have also an absolute maximum right there at that point, which is negative 2, 1, 2, 3, 4, 5, 6, 7. So at negative 2, 7, we actually have an absolute maximum. So it's okay to abbreviate abs max and abs min, rel min, and stuff like that. Let's see. Now here, let's think about what's going on in the extremes. As x gets really, so domain and range, it's a continuous function. Like this is an open circle, this is a closed circle, so it does pass the vertical line test. There's no holes in the function. So for the domain, we can say that the domain for x's consists of all real numbers, and the range now is going to consist of y's that are always going to be less than or equal to 7. Because all the y's, the most that y can get is a 7 every other place on the graph. Well, no, that's not true. Over here, as we go to this extreme over here, this keeps on going upwards. So the range and there's no place down on this one. Like this is the lowest point on the graph here. So y is going to, on one end, range to positive infinity, and on the other end, the lowest it's going to get is a negative 3. So again, we're using interval notation. A square bracket means it can be equal to a negative 3. And then rounded bracket means it can head towards infinity. It's heading towards positive infinity as you go on to the other end. So we put a curved bracket on that. So that's how we would use the interval notation to talk about what y does. Y can go all the way down to a negative 3 and equal negative 3, and then y can head all the way towards positive infinity. And in terms of the range, basically x's can be any number at all. So I think we've took care of everything that goes on with number 13, 14, and 15. Anybody have any questions on that? So don't get bogged down in the notation. If you're not sure about the notation, just write it out in words. But basically, you got to think about all the different parts. Like on number 13, there's 3 main things we need to think about: what's going on at each end and what's going on at the point in the middle where the maximum is. For number 14, there's 3 points in the middle that we have to worry about: the maxes and the mins. And then we also have to worry about what's going on at either end. So there's 5 things going on with number 14 that we need to consider. And then for number 15, we've got what's going on to the left, what's going on to the right, and you've got a maximum and a minimum. So you've got 4 things to worry about for number 15. Okay, let me go on to the next set here. So number 16, we can kind of see that here we have a relative minimum. Now, it's not an absolute minimum because this line here is going to keep on going. Let's see if I can use my magic pen here. So this line here is going to keep on going in that direction. This is going to keep on going in this direction. Now, if we thought about this, this is actually an S-type shape. So this is some kind of a third degree equation that actually generated that, if we needed to think about what family it was in. The other thing is, let me get back to regular pen here. Oh, what did I do? Got stuck on my... Get back to regular pen. So as x gets really large, y is going to be getting really large. So as x gets really large, as x goes to positive infinity, maybe this is the best notation. The limit as x goes to positive infinity of y is positive infinity. Y goes to positive infinity. So I'm just kind of, putting some symbols in here. The limit, so as x travels and gets bigger in the positive infinity direction, y gets bigger in the positive direction. As x gets really big in the negative direction, so the limit as x goes to negative infinity, and again, pretend you're kind of traveling along the line. What's going on with the y's? The y's are getting smaller and smaller, so y goes to negative infinity. So that's how we can talk about the extremes there. And here we have what would be actually a relative minimum at -1, -2, -3. At -2, -3, you have a relative minimum. It's not the absolute minimum. It would have been if this piece here wasn't heading all the way down. Like if this kept going up this way or off to the side, then this would be an absolute min. But because of the graph, it's a relative minimum. Okay, so that was 16. Let's look at 17. So on 17, we got, okay, continuing on, that's going to keep going that way. That's going to keep going this way. So as x goes to positive infinity, y goes, and sometimes I like to use delta to kind of be the movement as x changes and goes towards positive infinity, y changes and goes towards positive infinity. That's what's happening over here. What's happening on this side is as x goes to negative infinity, y goes to positive infinity. So that's what's going on at the extremes. Here we have a absolute minimum. Notice the rest of the graph is all higher than this point. So this is a absolute min. And its location is at 1, 2, 3, -1, 2, 3, 4, 5, 6, 7, 8. So 2, 3, 4. Yeah, so 3, -8. And here we have a relative maximum at 1, 2, 3, 4, 5, -2. That's a relative max. And here we have a relative minimum. And again, the reason it's a minimum because over this area of the graph, this is the lowest point, but it's not absolutely the lowest point because you got this point down, this section of the graph down here that's below it. So that makes it a relative minimum. And the coordinates are 1, 2, 3, 4, 5, 6, 7, 8, -1, -2, -3, -4, -5. So at 8 and -5, you have a relative minimum. And those are all the key points on the graph. So looking at it, you've got the 3 turning points, the maxes and mins, and then you've got the behavior at each end of the graph. So you've got 5 things to consider for number 17. Did anybody have any questions on those? Everybody's good? Okay, looking at number 18 now. At 18, you can kind of see that this in the middle is kind of there's a balancing point in the middle. This is an odd function. This is an x to the third. There's this symmetry about the origin. Actually, at the origin, and we haven't really talked much about this, but a little bit of an advanced concept is this is called an inflection point. And at an inflection point, you can kind of see, like, let me go back to and change pens here. At the inflection point, you can kind of see that the graph is changing from, this is like what we call convex down, because it's this part of the graph is kind of like this, but this part of the graph is like this. So at this inflection point, it's changing from concave down to concave up at that turning point there. So that's why it's called an inflection point. So that's kind of like, that's something that's more advanced concept, but that's something to, kind of think about. And if you can see that, you can kind of incorporate that into the description. Now, as x gets really big as x goes negative, more and more negative, we see that y goes more and more negative. So for the, in the limit as x goes to negative infinity, y goes to negative infinity. As x goes to positive infinity, which means heading this way, y is going towards positive infinity. Y gets bigger and bigger. So I've intentionally kind of mixed the notation a little bit just to kind of get the idea across. Like, there's not just one right way to write this, but the idea is right now on this, we just want to be able to think about what's going on trend-wise as x gets really big, as x gets really small, and try to notice any key points that are in the graph. Now, if we were, if you guys end up taking calculus later on, this inflection point is easily found by taking the second derivative. You take the derivative one time and then the derivative the other time. So this is kind of how if I have a y is equal to x to the third type curve there, the first derivative is going to be 3x squared. I do this and then bump this down one. Second derivative, which is this one again, is going to be 2 times 3, which is 6, x to the first. So if I set 6x equal to 0, I get x equals 0. So at x equals 0, I have an inflection point. And setting this equal to 0 is places where I would have to consider that there might be maximum or minimum points. But we can see from this one, from the graph, that at x equals 0 for the first derivative, it's not a maximum or a minimum point, but it does happen to be the inflection point. So generally, first derivative with calculus, you can set equal to 0. You can find all the points where the maximum and minimums are going to be, and then you have to test them and see what they are if you don't have the graph to look at. Second derivative set equal to 0 will give you any inflection points, but you still have to check and see what's going on there. So, and what's going on here at 0 is we can see that the graph is kind of going from concave this way, and it flips around, and now it's going up, and it goes right at that point is where the change occurs. That's why they call it an inflection point. Okay, so that's, if you can see what's going on with that, you can include that as part of your description, but you don't really have to. But if you go further in math, that might be something that you're going to have to be able to deal with. For 19 through 22, they want us to use a graphing calculator and graph each function and determine and classify the extrema. Let's see. So I guess, yeah, there's no way around this one. We just need to try to do the graphing calculator on this one. So I'm going to bring up another window and go to Desmos. Back to the page and see what our equation is. So we got negative. Now, if we turn this around and get it in more standard form, the negative, this is, I like to do plus opposite when I have subtractions. So just to kind of, because now when I move the x squared, the negative can move with it. And this is, this is actually a negative 4 that way. So we actually have a negative x squared plus 3x minus 4. So a good habit is to always try to write everything in terms of descending powers of x. These other ones are all pretty much set up okay. So that's what I want to type into Desmos, negative x squared plus 3x minus 4. So we want to do negative x squared, or y equals negative x squared plus 3x. Now I got to do the down arrow to get away from the superscript. Plus 3x minus 4. So there's our graph. Y is equal to negative x squared plus 3x minus 4. So can I write on here? So classifying the extrema now, you can see that, like number-wise, okay, let's zoom in and see if we can figure out what this is. It looks like it's a little bit before 1. So I would say I would estimate like at right around 1.75 and negative. Okay, here we have, with Desmos we can just click the point. So at 1.5, negative 1.75, we have an absolute maximum. And then we can see that as x gets really negative, y gets really negative. So that's one extreme. And as x gets positive, y gets negative. So at the extremes, we've got y going to negative infinity as x goes to negative infinity and as x goes to positive infinity. And the absolute maximum of the graph is at 1.5 and negative 1.75. That's the vertex of the graph. And we could kind of make sense, like we can see that this is going to be an upside down parabola. And if we were factoring this, which is what's coming up in the section that we're on with 4.2, we would, using the quadratic formula, we would see that this would be a graph that would not have any roots. It would be one of those that if we did the discriminant, the square root part, b squared minus 4ac, the square root of that, we would actually get a negative number out of that with the a's, the b's, and the c's, which would tell us that the graph does not cross the x-axis. So that would be information we could get from the trying to do the quadratic formula on it. Okay, let's look at one of the other ones on here then. Let me go back. So now this is going to be a third degree. It's going to have some kind of a dip in the middle, but it's basically going to be a sideways S that we can see with number 20. So we've got w to the third minus 7w minus 6. So let me turn this one off. So we have y equals w to the third minus 7x. Well, let's use x. So on Desmos, it might be better to change your variables into x's and y's. X to the third minus 7x minus 6. Let me double check, make sure I had that. W third minus 7x minus 6, okay. So we can see, let's do the extrema first. As x gets really big this way, y gets really big in the positive direction. So as x goes to positive infinity, y goes to positive infinity. As x goes to negative infinity, y goes to negative infinity. So that's the two extrema. At this point here, which is negative 1.528, 1.128, we have a relative maximum point. And at this point here, at 1.528 and negative 13.128, we have a relative minimum point. It's only relative because at the extremes, the graph keeps on going in the negative and the positive direction to infinity. So that makes these just relative points, relative maxes and mins. And in the interest of saving time, let's look at the other ones, and maybe we can just talk about these. So same kind of a thing is going to go on with this one. It's an x to the third. It's got a square and 5x in it. So I would imagine that it's going to be something like this. And the same, you're going to see basically the same idea on the, now, yeah, you're going to have like the same idea on the graph. You're going to have like a relative max and a min. You're going to have positive infinity for the y's as x goes to infinity, and you're going to have negative infinity for the y's as x goes to negative infinity. Number 22, it's a fourth degree, so it's sort of going to be like a parabola with a flattened out bottom maybe, but this is going to cause a bump. So it might be something like that. And so you're going to have a relative maximum there, you're going to have relative minimums there, and you've got the extrema. So this is just kind of using the family idea of what the graph is going to look like. This is probably one we should actually go ahead and type in. So let me do that in Desmos, and we'll see how it actually looks. So let me take a look at it again. So we've got x to the fourth minus 4x squared minus 2. So y equals x to the fourth minus 4x minus 2. So x to the fourth minus 4x minus 2. And let me turn off number 2 here. Okay, so let's see what's going on. So with this one, we don't have that bump that I thought was going to be in the middle. Actually, kind of causes this weirdness here. It isn't actually a bump, but you kind of see that it kind of changes curvature a little bit. So somewhere in here, we're going to have an inflection point. But we won't really worry about that. That's not really one of the extrema. But down here, we have an absolute minimum at 1, -5. And as x gets really big in the positive direction, we can see that y keeps on going. So y goes to positive infinity as x goes to positive infinity. And as x goes to negative infinity, y goes to positive infinity. And then we have an absolute minimum at 1, -5. And somewhere about halfway in here, we're going to have an inflection point. Like maybe right in there, we're going to have an inflection point. Because you can see it's kind of curving this way, which is that concave up idea. And over this section, it's going to be like a concave down idea. So somewhere in here, it kind of switches. And then it heads down here, does an absolute turnaround, and goes up. So that's what that one would look like. So my idea was a little bit off. Like I was thinking it had something like this in the middle, but that extra stuff in the middle more added like that little bit of a, so this part here kind of turned into this. So it's unless until you do some of these, you get, the more you do, the more intuition I think you're going to have on what they look like. Okay, so determine and classify the extrema. So we kind of talked through it. I didn't really list it, but that's what's going on with that. And okay, this critical point maximum minimum idea, or should I go on the next page here? So what I want to do for number 26 then is think about what's going on either side of 0. So if I put so at 0, we're going to have the value 0, 0. So y is going to be a 0. At, say, -1/2, if we put a -1/2 in there, 5 times a 5 is a 25 times a 5 is a 125. We're going to have 0.125 for the y. When we cube, we're going to have -1.25 for the y. So when x is a -5, we have -0.125. So we can kind of see that on this side of 0, the y's are coming up. Okay, let's see what's going on the other side of 0 at 0.5. At 0.5, if I cube that, 5 times 5 times 5 is 0.125. That's positive. So at positive 5, the value of y is going to be positive 0.125. So as we pass through 0 towards 5, y keeps going up. So we've got this situation where it's increasing through 0 and it's increasing on the other side of 0. That makes this an inflection point. Let's look at 27. So for 27, let me switch colors here. We can see that this is an upside down parabola. So, but let's see what's going on at x is equal to 4. So I'm going to do this number line idea again at 4. And I want to check maybe, we're doing squares, so maybe check at 3 and check at 5. So at 4, a negative 4 squared, this is going to be a negative 16. This is 4 times 4 negative, so negative 16 plus 32, that's going to give me a positive 16. Take away 10 is going to give me a positive 6. So at 4, we have a 6 for the y value. Let's see what we get at 3. If we put a 3 in, we have negative 9 plus 24, which is going to, a negative 9 plus 24 is going to give us 15, and we're going to take away 10, that's going to give us a 5. So at 3, we're going to have a 5. And let's see what's going on at 5 then. 5 times 5 is 25, so negative 25 plus 40 is going to be a positive 15, and a positive 15 take away 10 is going to be a 5. So at 5, we also get a 5 out. So we can kind of see pattern-wise that y's getting bigger as you get to 4, and then it starts going back down again. So pattern-wise, that's got to go with a maximum. So there's a maximum point there. Now it's probably an absolute maximum based on it being an upside down parabola, but for sure we can say that there is at least a relative minimum point there. And pretty much that's what we would need to do for the other ones. Like here they're telling about negative 2.5. So I would again do the number line, say for 28. So this is 27. This is 26. We won't have time to do all of these. But say at 28, we've got this negative 2.5. So what I want to do is think about what's 3 and at negative 2. We want to see what's going on. So at 2.5, we're on 28. At 2.5, now 2.5 is a little bit harder. 25 times 25 is 625. So we get we get positive 6.25 out of that. We're going to double it. So we're going to get like 12.5 plus, well, 12.5 take away 25 is going to be like a negative 12.5 minus 7 is going to be negative 19.5. So it's really better to do these on paper than try to do it in your head. But this is what I'm thinking we're getting out of that. Whenever I do stuff in my head, there's a big chance of making a mistake. Let's see what's going on with the negative 3. You put a negative 3 into 28, you've got 2 times 9, which is 18. Take away 30, that's going to be negative 12. Take away 7 is going to be negative 19. So at negative 3, we have a negative 19. And then let's see what's going on at negative 2. A negative 2 times a negative 2 is a positive 4. 2 times 4 is 8. 8 take away 20 is going to be negative 12, and then we're taking away 7 again. We're going to have a negative 19. So at negative 2, we get a negative 19 for y. So trend-wise, let's look and see what's going on. We've got a negative 19, then it's going more negative to negative 19 and a half, and then it's heading back up again. So y is heading down when it gets to the 19, and then at negative 2.5, it hits the lowest point, and then it heads back up again. That makes this a minimum point. This was a max, this was a min, and this was an inflection point. So this is a easy way to test. Well, it's not easy because of the numbers necessarily, but this is pattern-wise a way to check for, and this is actually what you do in calculus. Once you get those critical points, you really need to check what's going on either side in terms of how the slope changes, or how the numbers change. And you can kind of see that it kind of changes a little bit, but it keeps going in the same direction. That makes it more like this kind of a pattern. With this one here, it's reaching the top and then heading back down again. That makes it this kind of a pattern, which is concave down, and this is concave up. It's a little bit higher here, hits the bottom, and then heads back up again. So these would kind of be relative to the graph where those 3 points are. Relative to the graph, that would be where these 3 points are. So it kind of traces out the pattern. So we did 3 of these. That's what you basically have to do for the other ones. Like 29 might not be too bad because you got 0. So you need to check maybe -1, 0, and 1 and see what's going on pattern-wise. With number 30, same thing, a little bit less than 2. So a 1 would be a good one, and a 3 would be a good one. If you still can't tell, you need to check numbers a little bit closer to the value of interest, which would be 2. So you might want to check like negative, or take half away. So 1.5 and 2.5. But just to make the numbers easier, try doing like whole integer type jumps. And 31 is going to be even more work because you got a cube in there. So 3 cubed, with all that other stuff, do it on paper, see what you get, and then maybe check it for 2, and then check it for 4. And it's going to be one of these 3 patterns that you're going to see out of these. So that's the way to do those. And then let me see what I got on the next page here. And that's really the last problems on this page then. So we didn't talk about 3 of those, but you could do those in the calculator. Okay, so we didn't really do anything new with the 4.2 stuff. Let me save this, or get out of this anyway, and bring up the 4.2 problems. Okay, so here we have the 4.2 problems. My cursor. And trend-wise, and I go over this on the video that's linked to on the page also. There's a lot of stuff that we can kind of talk about just using this chart right here, which is like the first part of, it's right at the beginning of the chapter in the book, 4.2. So let's talk about what's going on with the discriminant. So I'm going to use the square root type notation here. So the key idea is that, and we can see from this graph that it's going to have 2 roots. There's 2 places where it crosses the x-axis. If when you simplify the b squared minus 4ac part, as you start into the quadratic formula, you end up with a positive number, that means you're going to have 2 solutions. You're going to have 2 real solutions. If it just touches at one spot, the graph's going to look like this. Now, this could be any place along here. This is like we've done these before. This would be like if that was the point -2 for x, this would actually be the graph of y is equal to quantity x plus 2 squared. That gives us 1 intersection point. There's 1 root. But the quadratic formula, when you do the discriminant part, the square root part, those numbers are going to cancel. You're going to have a 0 there. Whenever you see that pattern, you know you're going to have a double root. You're going to have 1 solution. It's going to be the same number twice when you try to factor it. And if you have a case like this where you see that it doesn't cross the x-axis at all, there are no roots. There's no real roots there. And that's what happens if you get a negative when you do the b squared minus 4ac part. That means there are actually no solutions. It cannot be done in terms of the quadratic formula because there aren't any roots to be found. When you're using the quadratic formula or factoring, and setting the factors equal to 0, you're finding the roots, which goes with where the graph crosses the x-axis. Where is y equals 0? It's equal to 0 when x crosses the x-axis. So, or when the graph crosses the x-axis. So if it doesn't cross the x-axis, you can't find a root, you can't factor it, it can't be done. So that's, picture-wise, that's what's going on with this whole idea with the discriminant. Now, in terms of number of roots total, if you have an x squared graph where x squared is your highest term, you can have 2, 1, or no roots, real roots. If you have an x to the third graph, you could have 3, 2, 1, or 0 real roots. So the exponent, the highest exponent in the equation, gives you the possible number of roots you could have. Generally, you're going to have less than that number, but there's a possibility that you could have that many roots. So you can see we're dealing with parabolas right here. 2, 1, or no roots are what could come out of that parabola. And here are the 3 different cases that we can see. If we're doing x to the third, there would be 3 possibilities. You might have 3 roots. It might be something that does this. 1, 2, 3, and you got 3 roots. Or it could be something where it just kind of does this and touches there and there. That's 2 roots. Or you could have one that goes like this. That's 1 root. I don't know if you could actually have one with no roots. So maybe with 3, maybe you couldn't actually have no roots with 3. But that's kind of like something to keep in mind. So completing the square stuff, let's talk about that. It says, write a short paragraph explaining how to solve t squared minus 6t minus 4 equals 0 by completing the square. Completing the square is like the quadratic formula. Actually, the quadratic, and there's the last problem in this set deals with deriving the quadratic formula from the completing the square formula. And we won't have time to do that today, but if you want to see that, bring it up in one of the other classes and we'll do it. But the method for completing the square is to, first of all, make sure you have only a 1 out here in front. So if there's no number, it actually is a 1. If there's a 4 or a 3 or a 2 out here, you've got to divide it out. This has to be a 1 before you start using the completing the square. The next move is going to be to move this number over to the other side of the equal sign. So I'm going to turn this into t squared minus 6t equals 4. So coefficient of 1 is important, and then you move number term to other side of equals. Next step, you're going to take this middle number, take half of it. Negative 6 over 2 is a negative 3. And you're going to take that negative 3 and square it. And you're going to stick that number in to that place. So a 9 goes in there. And to keep the balance, I throw a 9 on the other side. That's the key part right there. Other than making sure that you have a 1 for an exponent in front of the square term, that's key. You take half the middle term and square it, and add that number to both sides. Now what we've done by taking half of this and squaring it, we've actually made this into a perfect square trinomial. This is going to factor into t minus 3 times t minus 3. So it factors into t minus 3 squared. And on the other side, we've got 13. Then what we do is take the square root of both sides. So on the left, we're going to have t minus 3. And on the right, we're going to have plus and minus. Not just plus the square root, we're going to have plus and minus the square root. You got to remember that, of 13. Solve for t, add 3 to both sides. T is going to be 3 plus the square root of 13, or 3 minus the square root of 13. Now, The square root of 13 is between 3 and 4. 3 times 3 is 9, which is 4 away. 4 times 4 is 16, which is 3 away. So we're somewhere right around 3.5 for the square root of 13. So approximately, we could say 3 plus 3.5 is going to be about 6.5. And 3 minus 3.5 is going to be about a negative 1/2. So that's how we could kind of guesstimate at the numbers without having to resort to a calculator of what we would get out of that. So we've got two roots. And if I did this with the quadratic formula, the first thing I would do would be to do the b squared minus 4ac part, which is the discriminant. And for this one, the a is a 1, the b is a negative 6, and the c is a negative 4. Now they're not asking us to do that on this, but I just want to kind of show how the discriminant thing works with the quadratic formula. So if you wanted to factor this by using the quadratic formula, remember x is equal to minus b plus or minus the square root of b squared minus 4ac all over 2a. But this part here is the discriminant. We want to do that part first, always. So negative 6 times negative 6 is 36. Take away 4 times a, which is 1, times c, which is a negative 4. So you got to be careful on this part where, again, this is like a negative 4. A negative 4 times a negative 4 is a positive 16. And a positive 16 with a 36 is going to give me 52. So inside this square root, we actually have the square root of 52. The important thing, though, is this is a positive number. That means we're going to have two roots. And we can continue on with the quadratic formula. So x would be minus b, which would be positive 6, plus or minus the square root of 52 over 2. Now, this is going to give me 3 plus and minus the square root of 52 over 2. That's going to basically simplify to these same numbers that we got there. That's the way the quadratic formula would work. Okay, so that's all we really have time for today. Let me know going into next class if there's anything that you want to see worked, and I'll make sure I have it ready in notebooks so we can go over it.
Good morning, Mark.